It's an extension. Here we go. Today we're starting off on page 114 in our workbook. So those of you that have it, you're awesome. Those of you that don't, you're still awesome, but you have to follow along. Maybe write a little more.
Yeah.
All right. So our textbook refers to this as the rational zero theorem. You will generally hear it called the rational root theorem, but it's the same idea. So this is a great example that talks us through how it works and why it works. So if you multiply the factors of this function, f of x equals x minus 1 times x minus 2 times x minus 3 times x minus 4, you can write the function in standard form. We know how to do that, right?
Yeah. Right.
So here's the factored form, here's standard form. Now, f of x is a polynomial, and it has integer coefficients. That's part of what it has to have to be a polynomial function, right? And it begins with the term x to the fourth, and ends with the term 24. And our zeros of this function, what would the zeros be? 1, 2, 3, and 4. Now, notice that each zero is a factor of the constant term. So my constant term is 24. And just to refresh ourselves, the factors of 24 are 1 and 24, 2 and 12, 3 and 8, 4 and 6, and that's it, right? So here's a list of all the factors. And if we look at our zeros, 1, 2, 3, and 4, are they in that list? Yeah, there's some other numbers in that list, but all the factors are in that list. Now, it asks us to consider a second function. G of x equals 2x minus 1, 3x minus 2, 4x minus 3, and 5x minus 4. So all they did was add some coefficients to these, didn't they? And so if we were to multiply all this back, we would get this function in standard form. G of x is a polynomial with integer coefficients that begins with the term 120 x to the fourth and ends with the same constant 24. And the zeros of this function are 1/2, 2/3, 3/4, and 4/5. So, in this case, the numerator of each zero is a factor of 24. Well, we've got those factors up there. Are the numerators 1, 2, 3, and 4? Are those factors of 24? Yeah. But the denominator of each zero is a factor of the leading coefficient, 120. Is 2 a factor of 120?
Yes.
Is 3 a factor of 120? Yeah. Is 4 a factor of 120? Yeah. Is 5 a factor of 120?
Yeah.
Okay, so all these zeros came from those factors. So this is a good example of the rational zero theorem or the rational root theorem. Whenever we have our polynomial function with integer coefficients, every rational, not every zero, but every rational zero of this function is a number in this form. It's a factor of the constant over a factor of the leading coefficient. Every possible rational zero comes from this list. Now the list may have extras that aren't, but all the possible rational zeros come from that list. So, it's a factor of the constant over the factor of the leading coefficient. And if you're taking notes, if you didn't have your notebook today, whoops, looks like I'm marking that out instead of highlighting it. A factor of the constant over a factor of the leading coefficient. So let's take a much simpler function, such as this one. And let's list all possible rational roots. Now, once again, everything in this list will not be a rational root. But this list will contain every possible one. So what we do is in the numerator, you put all the factors of -5. Well, we could do 1 and -5, right? Or we could do -1 and +5. So all the factors would be plus or minus 1 and plus or minus 5. Does that make sense?
Yes.
Okay, now let's look at the leading coefficient, 2.
2 and 1, and then negative 1.
Okay, plus or minus 1 and plus or minus 2. So this is how we set up our fraction. Now let's simplify it. If we take these two numerators and divide them by 1, do they change? No. So it's plus or minus 1 and plus or minus 5. But when we take these numerators and divide them by 2, do they change?
Yes.
Yeah. So that's where we get plus or minus 1 divided by 2 and plus or minus 5 divided by 2.
Oh.
So this is a list of all the possible, yeah,
No, 0. Oh.
all the possible rational zeros.
Was there a question like that on the quiz?
No,
Something like that? No.
not yet.
I think
didn't
it's
do
like
that
all
to you
the
yet.
zeros.
It was all the zeros.
All the zeros.
Yeah. Not, no, I'm, yeah.
Right.
Yeah, I'm pretty sure I messed it up too.
Yeah.
I think I
I
got it.
messed up.
I was so
I got that one.
confident going into it. I don't know what happened.
It's alright,
3 and
Caroline. We're
6,
stuck
I
with
messed
it.
up.
It's normal, right? I felt everything last week.
All the graphs
Hey,
I was
hey.
fine.
I'm glad last week's over for you then.
Yeah.
You had a long weekend to recover and you're fresh and ready to go.
And now you're
Yeah.
Everybody makes
right on
mistakes.
track.
Everybody knows what.
Ryan, I like your
Alright, so if C over B is a rational zero of a polynomial function p of x, explain why bx minus c must be a factor. So if this is a rational zero, then c over b will equal 0. Well, excuse me. Well, c over b has to equal x because that's where we get our rational zeros from. When we say x equals 2, x equals 3, x equals whatever. So if we took this and we solved for the 0, we get c equals bx. And so we get 0 equals bx minus c. So if this shows it is a 0, then bx minus c must be a factor of that polynomial. May not be the only one. Okay, so we already know this, don't we? We actually did it in terms of a and b instead of b and c. But you guys know how we do negative b over a. This is the same thing, isn't it? Okay.
Okay.
All right. Let's flip over to example 7. All right. In this one, we're going to use the rational root theorem to identify the possible rational zeros. The constant term is 12. So here's all my factors, right? 1 times 12, 2 times 6, 3 times 4. That's everything that is a factor of 12. Now, in this one, what is the leading coefficient? 1. So what would the integer factors of the leading coefficient be? Plus or minus 1. So 1 times 1 is 1, and negative 1 times negative 1 is 1. Alright, so we're asked down here to find all the possible rational zeros or rational roots. So we do all the factors of the constant, which are plus or minus, and I'm going to just put the plus or minus at the beginning right now. And we're going to divide that by all the factors of the leading coefficient, which is the understood 1. Well, if we take those and divide by positive or negative 1, does it change the list at all? No. So this list, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. If there is a rational root to this function, it's in this list. All rational roots are listed right in there. Now, are all of these actual rational roots of the function? No, this is our list of possible. That's all our possible rational roots. Okay, now, we're going to test some of these until you find one that is an actual 0. Okay, guys, if it's an actual 0, what will the value of the function be?
0.
0. So one way we could do it is to plug in, what are they asking us to test? 1 and 2. Let's find the value of f of 1, and let's find the value of f of 2. So if we plugged in 1, f of 1, we get 1 cubed minus 1 squared minus 8 plus 12. Well, that's 1 minus 1. Those cancel, right? And negative 8 plus 12 is 4. Not negative 4. 4. So, is 1 a 0? No, because when I plugged in 1, did I get out 0? No. The function doesn't have a value of 0 at 1. Now, look what's going to happen if I test 1 here. If 1 were a 0, what would the remainder be? 0. But we know that 1's not. We just did it. But let's see what happens. Bring it down. Multiply. Add. Multiply. Add. Multiply. Add. Add. Did I get 0? No. I got 4. Hey! What did I get up here? 4. So not only did this not give us 0, so we know it's not a 0, what it did give us was the remainder. Yes, sir.
So you can test to see if it's an actual 0 through plugging in and synthetic division?
You can,
Oh my.
but I wouldn't do both
Oh, that's just crazy.
unless you actually got 0. Because this doesn't help us. There's nothing we can do with this. This just tells us 1 doesn't work. But so did this. Didn't this tell us 1 is not a 0? Yeah. Okay, so now let's plug in 2. Let's find f of 2. So 2 to the third is 8. 2 squared is 4. 2 times 8 is 16. And let's see how that works. Okay, so 8 minus 20 is negative 12. Plus 12 is 0. Okay, so I know that 2, using the remainder theorem, I got a remainder of 0, which tells me that this is a 0. So I should get 0 there if I do this right, shouldn't I?
Yes.
Better.
All right, you finish it.
So, go ahead, Matt.
He's just done.
Okay, so for all of the possible zeros, we can plug all of them into the equation and find the actual zeros.
You could, but you don't always have to plug them all. You'll see in a minute. Sometimes there's quicker ways.
Wait, I didn't get 0.
Uh-oh.
You didn't do it right.
Okay, bring down 1.
Oh, I didn't bring that
You
one.
got
Okay. There we go.
2 and negative 12.
Look tired.
I've had it.
Oh, I'm sorry. Have you been drinking enough water? All right, 2 times 1 is 2. So this gives us 1. This gives us 2, which gives us negative 6, which gives us negative 12. Ding, ding, ding.
0. Oh.
Okay? So we kind of have a check there for us. That's kind of nice. So since this worked here and here, we know that 2 is a 0. And if 2 is a 0,
Plus or minus?
what must be a factor of that function?
Negative 2.
X minus
X
2.
minus 2.
Yeah, the opposite of that. X minus 2.
So close.
Okay, so let's keep going. So we know that x minus 2 is a factor. Well, what are we left with right here, folks? If we took a cubic function and divided out x minus 2, we're no longer left with a cubic, because we took the x minus 2 out. What are we left with right here? A quadratic. This is x squared plus x minus 6, isn't it? So when we factor out that x minus 2, we're left with x squared plus x minus 6. Whenever we're left with a quadratic, we are good. Because quadratics will either factor or, exactly what John said, we can use quadratic formula. I'm going to try to factor first every time because factoring is kind of nice. Do you see that this factors to x minus 2 times x plus 3? Okay.
Can we do x minus 2? Oh, we're doing linear.
So my factors are this. I have 2, which I can call a double. We have a double 0 at 2. And then we have another one at negative 3. This double at 2 tells us what's going to happen on our graph, doesn't it? Okay? Because it says how many times? Once we get multiplicity at a root, 2 is twice. Because we have multiplicity out the root, it's not just going to pass through with a straight line. Because it's even multiplicity, it's going to do what? Bounce. It's going to be tangent there. And negative 3 does not have multiplicity, so it's just going to pass through. So we have this multiplicity here at this root of 2. And because of that, it will be tangent. And then at our other, we just have negative 3. So it just occurred once. So there's no multiplicity at that root. It's just going to pass through with a straight line. All right. Now let's check out degree and leading coefficient. It is a cubic polynomial with a positive leading coefficient. What am I in behavior going to do?
Opposite. Well, it's going to go up to infinity.
It's going to go like that.
Is it going to rise or fall from right here?
Fall.
Fall to the left and rise to the right.
That's right.
Okay, so it's going to fall to the left and rise to the right. They did theirs backwards for some reason. Okay, we know we're going to pass through here. And we're going to bounce here.
Good job, okay.
We got it? Okay. Last example. Nope, not second to last example. Sorry. Flip on over to page 116. Let's look at number 4. Okay, step 1 is to list our possible rational roots. Okay, we need the constant and we need the leading coefficient. The constant is 3. So what are the factors of 3? 1 and 3. Our leading coefficient is negative 1. What are its factors?
Negative 1.
Plus or minus 1. So my possible rational roots are plus minus 1 and plus or minus 3. Correct?
Yes.
So.
Okay. So let's pick one of these. You want to start with positive 1?
Yeah.
Alright. So we evaluate the function at positive 1. If we get 0, we know it's a 0. If we get anything else, that tells us that's the remainder, right? Because we're using the remainder theorem. If we plug in 1, I get the opposite of 1 to the 4th, so it's negative 1. Plus 4 times 1 is 4. Minus 2 times 1 is negative 2. Minus 4 plus 3. Okay, so this cancels with this. Negative 3 plus 3 is 0. I know, I can start my division. My first rational root is 1 because it worked. Alright, I'm going to do negative 1, 4, negative 2, negative 4, 3. Okay, just finding 1 is not going to do enough for me this time, will it? Because this is a 4th degree polynomial. If I divide once, that'll just leave me with a cubic. So in a minute, let's go back and see if we can find another one. Alright, so let's bring it down. Multiply, add, multiply, add, multiply, add, multiply, add. You know what? I bet you could factor this one at this point. But you can't always. This one does factor. But I'm going to show you what to do. Like, when we go back and look at the first one, usually with 4 term, don't we take the first 2 and take out what they have in common and look at the second 2? Would that work on this problem? No. No. So, if factoring works, you should do that. Because factoring's easiest. But sometimes factoring doesn't work. Factoring actually would work at this point, but I'm going to pretend like it doesn't. And test the next one. If we plugged in -1, let's evaluate. F of -1. So we get the -1 minus 4 minus 2 plus 4 plus 3. So the 4's cancel and I get -3 plus 3 is 0. Woo! -1 works.
Good job, Mateo.
All right, so let's try -1 now. You try.
Oh, it works.
All right, did you get 0?
Yeah.
Awesome. So what we're left with now is a quadratic. Because we took a quartic and divided it twice, so now we have a quadratic. So we could take this quadratic and factor it. We can factor out the negative. And then it factors to x minus 3 times x minus 1, right? Now, could you write the complete factorization at this point? You sure could. This function was f of x equals, we just factored out the negative, don't we? We got these two already. So we got negative x minus 3, x minus 1. Okay. This would give me an x plus 1, right? What would this give me? Another x minus 1, but I've already got 1 listed, so that one would be squared, wouldn't it? So my zeros, which I probably should have written before I did the complete factorization, I've got a double at 1. What does that tell me about what's going to happen there at 1 on the graph? It's going to bounce. And then I've got 1 at -1 and 3. Now, that remainder theorem is pretty handy at showing us which ones are zeros. If we get a remainder of 0, we know that's a 0 of the function. That's what the value of the function. If we get anything other than 0, we're not going to do synthetic division with that number. Do you have to do both? No. You could go straight to testing each one of these in synthetic division. But anytime you get anything other than 0 down here, you've wasted your time. All right. This is the last example. All right. Give me a list of the possible zeros. See if you can do it. It's the same page, right? Down at the bottom?
No, it's 118.
Oh, okay. Sorry. 118, folks. Hey, can you guys also check to make sure none of you accidentally packed up one of my class set of calculators? That happens sometimes. I've got one that's gone MIA.
Never do.
As long as it comes back in the next day or so, we're good. I'll leave them out, but if it doesn't come back, I'll have to pack them up.
Is it like this number 16?
It may be. I haven't double checked to make sure all the calculators are in the right spot. But thank you. I appreciate all you checking. All right. So factors of 12 are 1, 2, 3, 4, 6, and 12. Now, when I divide them by 1, none of them change. But when I divide them by 2, I also add in 1/2. 2 divided by 2 is 1. It's already in the list. We're good. 3 divided by 2 is 3/2. 4 divided by 2 is 2. It's already in the list. 6 divided by 2 is 3. It's already in the list. And 12 divided by 2 is 6. It's already in the list. So here's the list of possible rational zeros. So these are our list of possible rational zeros. So we just got to start trying some.
Are those
All right.
plus or minus, or all they are?
They're all plus or
That's what
minus.
I
I'm
thought.
just being a little lazy with
Okay.
my list. Okay. For sake of time, I'm going to tell you that plus and minus 1 do not work. Girls, try positive 2. Gentlemen, try negative 2.
It's 16. 2 to 4, it's 16.
Ladies, did positive 2 work? Yes. Gentlemen, did negative 2 work?
Yes.
Yes. Okay, cool. Because if I start with a quartic and I divide it twice, I'm down to a quadratic and things are good. Now, if you had tested positive and negative 1, you would have found that you didn't get 0. You would find a remainder for each one of those. But for sake of time, I told you which one to start with. So we're going to start by doing synthetic division with 2. And then we're going to do synthetic division with negative 2. You try.
What does the synthetic division here do? Is it just double checking?
The synthetic division gets us down to the quadratic so that we can factor it.
Okay. I got you. Yes, sometimes I do.
Matt, you're trying.
Making sure.
Wait, I thought it was just equal to 0. You didn't say that.
Gotcha. This will give you 4, negative 1, negative 2, negative 13, negative 26,
Oh,
negative 6, negative 12. If you need to check your first line, it's up. Yes, sir.
Would I have gotten different numbers if I had started with -2?
Certainly.
Okay.
But our next line will match. If
Okay.
you did negative 2 and then positive 2, and I did positive 2 then negative 2, that next line has to match if we both did it correctly.
Oh, so you can do it in any order?
Oh, yeah.
Okay.
You can start with any rational zero with synthetic division. All right, so we bring down the 2, we multiply, we add, we multiply. Hold on. We multiply, we add, we multiply, we get 0. So, Sid, even if you did it in the reverse order, did you end up with this quadratic?
Yes.
Yes. And how is this going to factor? Well, trial and error, we'll start with the 3 because there's only one way to get it, 3 and 1. So we need 5 now. So if I did 2x, nope, that's not going to do it. Yeah, it will. Yeah, it will. I need 2x here, and I need x there.
Minus.
Yeah, that
No,
works.
no, no.
And then
minus
a
3
neg
positive
x
1.
minus 3 and then 2x plus 1.
It works.
No, you need a negative 5, so this needs to be negative, doesn't it? That gives me the negative 6.
Not
Or you could just do x minus 3.
Oh, minus 3, yeah. I like that. I'm sorry. You are correct. I am incorrect. X minus 3 and 2x plus 1.
Oh, I see.
Okay. So if we want a completely factored function, well, we just got 2 of them. X minus 3 and 2x plus 1. What are the other 2?
X
Negative
plus
2
2
and
and
positive
x minus 2.
X plus 2 and x minus 2. So what are my actual zeros?
3,
3, negative 1/2, and plus or minus 2.
negative 1/2, 2, and
Yep.
negative 2.
Good.
How come we don't do that with like the whole list of possible zeros? Like we
This is
only did
champion
like the
range.
synthetic division stuff for 2 and
We only did it, okay, we only did it 2 because we started with a quartic, and if we divide a quartic twice, we're down to a quadratic.
okay.
Now, we could keep testing and keep doing synthetic division, but we don't have to because we know how to factor a quadratic.
Okay.
Okay, the first 2 on your homework are just by factoring, so you don't forget. You know how to do that. The next 4 are doing what we talked about today. You're going to identify all the roots of the equation. We call them roots now because do you see they equal 0 when they're not functions? When it's a function, we call it a 0. When it's equation, we call it a root. Okay, so we're going to, same thing, and you're going to give the multiplicity of a root. So if it's a double, if it's a triple. Okay? All right, and that's all you have. You really only have 4 to practice what we did today with. Yes, sir.
When you go